in the Mid-Atlantic, but I have experience in agriculture elsewhere, including New York State, where I did some my initial studies, then through Madagascar to Ethiopia, and now to Maryland. So, and actually with Pennsylvania in between. So what I came over to UMES, I started work on our project with bioreactors. And so these bioreactors were initially introduced in the Midwest, and a project was opened up through Virginia Tech to take a look at some different bioreactor types. And to begin with, these bioreactors are looking based on a practice developed it by NRCS, practice 05. So these particular ones are not not very simple. They're a bit more complex, and with that complexity, the cost goes up. But the idea is that we're looking at different integrated approaches to reduce nutrients into waterways and eventually into the Chesapeake Bay. So the collaborators are varied, including UMES, Virginia Tech with Dr. Zach Easton. He's basically the professor who developed the idea for the proposal to be able to do this work. USDA ARS up at University of Pennsylvania, my former employee. University of Illinois, where one of the bioreactors was basically designed for implementation down in Westover, Maryland. And then also the Midshore Riverkeeper Conservancy that has offices in Easton, Maryland. So this is the standard that I talked about. So they're called Denitrifying bioreactors. And in this particular one, it's the idea that it's water coming from tile drains, which is prevalent in the up in Iowa, in where you have much larger field sizes. So the bioreactor is tied into a tile drain. The bioreactor itself is filled with wood chips that provide the carbon source for the denitrifying bacteria, microorganisms that allow for denitrification of the nitrogen forms in the water, and after denitrification, that water is then released back into the waterway with less of a nitrogen load. So it was only recently approved as a practice in 2015, again, Iowa, Ohio, and South Dakota. And with any practice, it may work in there really well. So the idea is if we have a serious, there's land that has serious nutrient problems or excess nutrient. So we were looking at possible practices to help mitigate those problem areas. Tile drains were diverted to the bioreactor. We have incorporated them into ditch systems. That is the main drainage practice around. Wood chips harbor the microorganisms for denitrification, and there was a 35 to 50% removal efficiency. So we went at the professor at Virginia Tech, he developed the proposal to look at these in Virginia and Maryland and now we've opened up some in Delaware to look at their effectiveness and to monitor them after installation. So since it's a conservation innovation grant, you actually have to have something to show for the work. So the implementation was part of the project, along with monitoring nutrients and the water flow and looking at the economics. So the economics is still ongoing. So the talk today is more about construction issues. They're monitoring what has been done and trying to move forward with either improved ideas or adjusting some of the practices that we have here, improving upon them, and seeing how effective they are in this region. And in the end, with some of the work that we're doing, we hope to expand the NRCS practice and develop that to be able to use in a broader area. So there's different types of bioreactors that have been implemented, and they're basically in the very near the Chesapeake Bay on the eastern shore, and then in Virginia. So we're going to discuss each of these, take a look at them. So just a brief rundown of denitrification. This is the goal that we're looking at. So if you look in the top left quadrant of that, so we're trying to take the nitrates, convert them into N2, which is what we are actually breathing right now. And during each of these steps, carbon is required. And that carbon source is wood chips that are being put into these bioreactors. And denitrification can be fostered by the anaerobic conditions brought about by more saturated conditions that we've developed through pushing the drainage water through these bioreactors, maintaining that anaerobic condition to improve denitrification. So another pretty picture. So what we're trying to enhance are these. Through these, we're able to, that denitrification process can continue going on. So these are some of the forms. The concerns in the environment are the nitrates and the ammonia as well can be toxic. So we're looking at ways to convert that to non-toxic forms. So the basic concept of bioreactors is that we're creating a habitat for this denitrifying microorganisms. So the organic carbon source, the wood chips, anaerobic conditions with the constant need for drainage, and for most times of the year that is easily maintained, and as electron acceptors for the NO3 ions. And in the end, we have the nitrate enriched water passing through the wood chips, the denitrification process occurring, and if you can extend the time of contact, then that process is able to work effectively, and then as the water passes back to the waterway, the ditch, the stream, then you have, you're hoping for, with all the cycling that's done, that a reduced nitrate to the waterway. And this is working on some of the systems, and either through being directly applied within the ditch or a diversion from the ditch, and drainage control being possible. Because an actual stream setting where you have vegetation growing and the water is able to move more slowly through the stream, that is actually allowing for denitrification as well. So one of our thoughts is to also look at just a natural stream or natural ditch system to see how well through water management we can actually reduce nitrates coming through through drainage management and through inlet and outlet controls. So the first bioreactor is an in-ditch stepped bioreactor. So it's this is the more pricey of the models, if you will. But it's one that was looking at larger farms with larger waterways, that it does actually reduce the amount of land that's needed because it's directly incorporated into the stream. So it took some survey work, and some of the cost was reduced through the excavation done by the land manager. So he excavated some of the stream to allow us to lay the perforated pipe that passes the length of the bioreactor. As you can see in this quick image, that's perforated pipe that will accept the water that has been that has gone through the process of denitrification. Here are the different steps of construction. So the steps come in to help control water flow. So it's just basically a drop flow setup, and the perforated pipe will pass through those steps. And over top of the perforated pipe is the wood chips. And those wood chips are, these were from the Eastern Shore Forestry Products company that's done in Kokomo. Since we were in Westover, that was very convenient for using those. The wood chips were spread out. Then stabilizing gravel was laid over top. Sorry. And the pipe outlets here. So the concept is get this set up. So this is water passing through the bioreactor. So upstream of the Jeep, we have the tile drains that are released into the ditch. The water flows, and there's actually just right to the upstream side of the Jeep, a flow control structure that would allow to stop water flowing in and keep water in the fields for irrigation purposes. So when the water is released, it passes through that large flume and into the first step. So the water infiltrates into the gravel, into the wood chips, and enters into the perforated pipe. If there's excess flow, so this is a low flow condition, if there's excess flow, that water would flow over the wood dam and be treated in the next step. And then again in the third step. So, and then by the end, we're working to treat as much water flowing through the ditch as possible. And we're monitoring this area with flow discharge levels and depth, and then also taking nutrient grab samples from from the different parts of the bioreactor. So the ditch diversion bioreactor. So this is one that is closest to the 605 documents. This has water coming into the ditch either from a tile drain system or just a traditional ditch system. There's a diversion box. So during low flow conditions, you have the majority of the water being diverted. During higher flows, in the particular one that we were looking at, it's 90% of even the high flows are being diverted into the bioreactor. It passes along a rectangular shaped bioreactor, and then comes out at the end back to the ditch. So diverted, treated by the bioreactor, and then released again. And so this is some of the construction details. And you can see that it's a large excavation. This one is directly parallel, maybe 10 to 20 feet from the stream. The stream is in the trees. And it's lined, the wood chips are put in, and then the water passes through. And this is the bioreactor completed, and now after a summer, the natural vegetation has kind of recovered over top, and you have grasses coming back, and it was back to basically a grassy buffer. And then the monitoring system is automatic samplers that we set up to during storms, because it's all fine and good to be able to handle low flows, but you also want to be able to handle the high flows during runoff events that are, and in this on this farm there were the reduction occurred in both events, but we're still in early stages of monitoring. A permeable reactive barrier is quite a bit different because it's not really hooked into any water coming directly. It actually is a trench that's filled with sawdust that parallels the stream. And so the idea is that you have your stream or ditch, and the trench runs the field length of your of that, and it's directly parallel. So the water draining from the field actually has to pass through the sawdust before it reaches the ditch. And in this case, you need to make sure the hydraulic conductivity, so the conductivity through this barrier is maintained. Otherwise, you can have backups. So that is through. You don't want excessive compaction on top of the sawdust to prevent the conduction of water through. But this was a novel idea for the really flat areas, especially on the UMES farm. As you can see, it's very flat, and these have been implemented on two. This is a Public Drainage Association ditch, as well as a main waterway, part of the Minokan watershed. So it's been excavated. It's maybe about this wide and filled with sawdust. And it was one of the coldest days that they implemented it. So that was before my time in UMES. So our monitoring system is a series of nested piezometers. So basically it looks like we have a crop of PVC. And it allows us to monitor water at different depths in the subsurface. Because of the high legacy on this experimental farm, there's been concern with movement of nutrients. Nitrogen, of course, has a high likelihood of moving in subsoil. But even phosphorus is moving more so via subsurface routes rather than its usual surface pathways. So the idea is that these allow for reducing nutrients in the subsurface. But if you're able to keep the top of these walls even or not, so there's no extra mounding, then the surface water can actually enter in as well, and basically drop in and then can be treated and move on to the streams. Here's a tile drain bioreactor that has this is the schematic, so the tile drain is almost a direct tie-in into the bioreactor, and it passes through something similar to the diversion, the ditch diversion, and so you have tile lines. So the tile lines run all the way to the ditch, and the bioreactor is placed there. So your sizing of the bioreactor depends on how much land is actually drained through the tiles. And here's a completed look at the bioreactor. And with biochar, which has been an emerging means for nutrient reduction, has been able to enhance nutrient removal incorporated with the bioreactor. And then this particular study was done at Virginia Tech, so they've been able to see some further reduction via the use of biochar. So now, to wake you up, hopefully, I wanted to, me being relatively new to the Maryland, I wanted to know, in the first time I did this talk, just this past hour, I wanted to know some of your experiences with drainage, and basically I should start out with, are you all from this immediate or relatively immediate area? So drainage is basically everything. Have you worked on, yes?
Well, the discussion, I was just wondering, has that been engineered to look at a 6 or 7 inch rainfall and 5 hours? You're putting them right beside the creek, or right down with the vehicle. So, where are you as far as engineering it to mass flood?
Well, that is a concern when you have the water flooding over and then flowing back into the bioreactors. Yeah, that is one of the things that we have found is a problem. So these particular samples have been implemented in a few areas, but in that case, that You would have to basically understand each site condition for the major flood areas, and to be able to design it where it's not going to be overtopped by floodwaters. But the diversion is only going to allow what the capacity is. So any diversion into a bioreactor is going to be controlled to treat the amount of water that it's able to control. So there would be bypass on that particular condition. So we're looking into those aspects.
But is there any difference in the type of wood chips, like hardwood versus softwood, or is there?
That, there has been studies. Right. But you don't want to have a wood chip that's going to change a lot of the chemistry of the water coming into it. So some wood is going to create issues in that way, raising or lowering the pH. Oh, just
How long are the wood chips going to last in there as far as denitrification? Do they have a limited life?
Well, the life,
The wood chips.
yeah, they talked about in some of the documents of 15 years, but I would be checking it in 5 years, and especially if you have the flooding issues where you're overtopping, then that's going to be even further concern. The other issue with some of the wood chips is because they have a lot of spaces in between, is the issues of channels being produced within and allowing direct flow from the ditch into that. So these were just, again, these are being researched as possibilities. They're not being, this is what we're looking at to see in issues of high nutrients, are there practices that, even at a higher end of expense, could they be possible in reducing nutrients? Yes?
With a couple of the different scenarios there with the diversion reactor, you can control the flow in and out. That's probably longer residence time in the filter media.
Yeah.
Are you seeing like a similar reduction from like that sawdust channel, where it's probably shorter residence time in that?
Well, you would think it would be a shorter residence time, but the lateral flow of water through the soil is really rather slow. So it's coming in. Yes, it would probably speed up through the sawdust, but it's still there has been actually good nitrogen reduction within the sawdust walls, but that is, again, a concern, especially with flooding, the flooding of water. So if a lot of certain storms, you're going to have an excess of surface flow rather than the subsurface flow. So that's, not going to be able to drop down into the, so, yeah.
You use the term sawdust and wood chips. Is there a difference?
Yes, the sawdust is a finer.
Right, I understand that, but with the porosity of the wood chips versus the sawdust, are you using one or the other in different applications of the?
Yeah, the sawdust wall that parallels the stream, that's where the sawdust is being placed. Wood chips are being used in the ditch diversion, the in-step or in-ditch stepped bioreactor, as well as the tile drain bioreactor. Those three are all wood chips. Yes?
What would be the advantage of the system versus like a plant riparian level? Is there any incentive to use this?
Well, the idea is that you would want to have both basically, because you're able to grow around it. So you would have a buffer, at least a grass area buffer. But the one thing with some of the buffers that is you're finding that there's concentrated flow paths that allow for bypass through the buffer, and then there's no other means of mitigation. So the idea is to, I mean, with some of these areas that are so seriously high in nutrients that the integrated approach is what we're looking at. So, yeah. Any other? Let's see. So, I guess, are you concerned with nutrient loss reduction? I mean, I would hope so if you're and dealing with my boring talk. In the cases of these bioreactors, what are some of the benefits that you might see that might be applicable to areas around where you are?
Well, we don't want to be a solution looking for a problem. We know there's a problem with nutrient loss, but in a particular field, do we know what it is? Is there enough data, or are there ways to go to high-risk areas and target, and then kind of explain what the options are? No, I'm not talking science here. I'm just talking about, absolutely applying this thing on a common sense level.
Yeah, I mean, basically in areas that you know have higher flow leaving from a field into a waterway, that would be one thing. I mean, the more.
We don't know what it is yet.
But if it's coming off of your field, that would be.
We think we have a problem, but we don't.
Yeah.
Really have a
Yeah. Yeah.
We need, in other words, what I'm saying is, maybe take a little bit more of a look at the high-risk areas and then determining what the load is. We've been thinking in terms of non-point sources.
Oh, yeah.
This is ridiculous.
Yeah.
If you have a high-flow area or a field that has overloading it, treat it as a point source, get some data, and now you've got a great solution for how to get out.
Yeah. So, yeah.
Doesn't have anything to do with science.
Well, it does. It actually does. Because targeting is, I mean, in areas, if you look at the flow coming from different areas, I mean, why wouldn't you put nutrients on a saturated area? Well, first thing, you can't get anything.
Can't get on it.
Right. Yeah, but the idea is also that is going to be the area where you have the highest connectivity to your waterway. Is if it's saturated, it's flowing as soon as it starts raining. So the idea then, if you're going to monitor it, I mean, there's multiple ways to be able to monitor an area that you feel is a critical area on your own land. And that's basically if you see higher erosion off of that land, higher flows, then you start thinking about, well, if it's erosion in addition to the water coming off of it, and you know you've applied nutrients, and through the calculations of the nutrients, you know you're you're giving that freeboard for uptake. Any excess is going to be gone with the water and through the subsurface. So those are particular areas that you're looking at, and collaboration with. If you're really interested, there's quite a few researchers who are interested in looking at areas to find and be able to understand, the variation across farms, to be able to help provide some possible solutions. So I think I think it's an equal effort on both sides to be able to approach this problem.
How long does the water need to stay in these systems to get the benefit?
In that, I guess it depends. It depends on the system that's being used. In the case of those that you're able to control the flow going into it, you would like to be able to ditch. You want to be able to have it provide enough time in the first step, so it's not overtopping every step, and you're getting the excess. But runoff events, depending on your runoff events, it's kind of, there's conditions that you can control and those are not. You try to enhance that time that it comes in contact. So it's actually quite variable. So we're looking at a lot of drawbacks with these as well. I mean, expense, complication in constructing them, the use of land that could be used for production. What are other drawbacks that you, yeah?
Majority of our land around here has little or no slope at all, so as far as collecting rainfall runoff into point sources like we're talking about, it's not the predominant situation. So most of our water is just percolating on site, not collecting in ditches or open waterways, so it's collected to a reactor.
Right, yeah. Yeah, but are there ditches that do drain to, because the water has to go somewhere. Is it to a ditch that surrounds fields or surrounds the farms, or?
In some cases.
Yeah. So in those areas, these are not, in some of them are the point source, but using the ditch or the as the point source. But others, with some of the parallel waterways that parallel the waterways, those may be more of a capturing that infiltrated streams. But then there's, in combination, you're going to have your field management that you're also controlling that excess being leaching down into the soil, because if it's leaching, it's not being used by your crops, and therefore that means losses of money in that way. These, as I mentioned before, are particular waterway practices on particular drained areas. So they're not necessarily point source all the time, but they're trying to kind of get at, more both the point source and some of the non-point. Other drawbacks or research interests? Okay, so some of the So some of the challenges and concerns that we've found, I mean, through construction, and these were divided amongst the particular types, but they may also be shared. These are definitely not any perfect solution, and they're not being touted as perfect solutions. They are being looked at as possibilities. And in this sense, these in-ditch, because you're excavating into the ditch, there was some issues of the sediment that was pulled out and placed on the line of the field. It actually helped to produce those concentrated flow paths that actually help to slough off the stream banks or ditch banks. And with the ditch diversion, the capacity is the issue. Is it going to handle those extreme storms that are more frequently occurring? The permeable barrier, you have the leveling of the surface to allow for some surface and the subsurface treatment of water. And with the tile drain, it's the flow through, because you have sediment, you have others that are going to possibly reduce the conductivity of the bioreactor medium. These are definitely not without their challenges, and there's many more that can be listed, but there have been positives, so we have been looking at those and looking at even entirely different types of practices to be able to treat water as it's coming into the ditches and tile drains. So some of the work has been published in extension articles. Virginia Tech has been the leader of the project, so the Virginia Cooperative Extension at Virginia Tech has a few publications. Denitrification management, and then denitrifying bioreactors, if you would be interested in more information. There's also a lot of different extension bulletins that have been published that might be of particular use in your situations. There's also, of course, the research publications, because that's a necessity. And some of the ongoing work is we're looking at continuing to look at nutrient removal over seasons and for the longer period, and also the greenhouse gases, to examine the economics more thoroughly, because the concern is, I mean, often it being a practice is cost as well as credits that might be possible, so looking at those. Adoption mechanisms, we've been able to show some of these to different groups, and developing targeting protocols and enhancing the practice standards that are already there, to see if there's things that we can learn that will be useful in more than just the region that it was initially developed, and then publish results in the various means that can get out to people who are interested.